First, let's clarify an important thing at the beginning. Here on the right side are our pins for connecting all sensors and probes on this control board. The currently active pins are highlighted in red. These are wired using standard DuPont connectors. Let's start in order. The probe pin is connected to GPIO 34. This specific pin on the SP32 chip does not have an internal pull-up resistor, but that's not an issue here. This controller board features a dedicated protection circuit for every input, consisting of both a protective resistor and a diode. The resistor limits the current while the diode protects against voltage spikes, making it much safer to connect your sensors via DuPont connectors. The Z-Touch or probe is wired as normally open. This is because the signal is only triggered the moment the bit touches the plate, closing the circuit. This contact signals the controller that the connection is made, allowing fluidency to accurately set the Z0 point. Wiring, X, Y, and Z axes, limit switches. GPIO 33, 32, 35 as normally closed is safer than normally open. If a normally closed wire breaks, the circuit opens and GRBL Hall stops the machine. With normally open, a broken wire causes a crash. In our YAML, don't use load because the hardware reads normally closed as default. X-axis and Y-axis just need PU for pull-ups, while Z-axis is clean. Download the YAML from my previous video if you have the same machine setup. For other configurations, you can modify it as you like. Here, we have the macro 1, 2, and 3 options on the board, which are mapped to pins GPIO 36, 39, and 13. These inputs are designed for physical control buttons, cycle start, feed hold pause, and reset. However, I am not connecting them in this build because I control the entire machine through the Gesender user interface. And now, we have come to the most critical part of the entire machine, the stop, or the emergency mushroom button. For this, we will be using the macro for input, which is mapped to GPIO 26. This pin has an internal pull-up resistor activated inside the chip, which is absolutely essential for the board to reliably read the state of the switch. However, when it comes to the stop, we have to pay special attention to how it's wired. To achieve maximum safety, our mushroom button utilizes two completely separate, isolated normally closed contact blocks inside it. Here is how the dual protection system works. The first normally closed switch is wired directly to your main high voltage power supply line, whether that is 220 volts or 110 volts. When you hit the button, this switch instantly cuts off all high voltage, killing power to the stepper drivers, the spindle, and the power supply. The second normally closed switch is wired into our controller board on GPIO 26. When pressed, it opens the circuit, instantly letting GRBL HAL know that an emergency stop has occurred, halting all software commands immediately. You must be extremely careful during the wiring process. The high voltage side 220 volts or 110 volts and the low voltage electronics side must remain completely isolated from one another. If the controller board, by some mistake or sloppy wiring, comes into contact with 220 volts or 110 volts, the board will instantly fry, release the magic smoke, and become completely unusable. Double-check your connections with a multimeter before powering anything up, keep those wires separated, and ensure your CNC is both smart and safely grounded. With that, we wrap up this tutorial. I hope I've made this easier for you. For more upcoming build adventures, don't forget to like and subscribe.